Hello, welcome back again to the lecture of offshore positioning of Institute Technology Bandung in Geodesy and Geomatics Department. Today I'm going to deliver about the last module. It's about the integrated inertial navigation system. As we previously already discussed about the inertial navigation system, we know that the inertial navigation system cannot stand alone by itself because of the drift that accumulated over time. And that's, we have to integrate it with another sensor. And we discussed in the previous module about how we integrate it and by means of coupling, for example, like what different kind of coupling that we want to choose to deliver our integration methods, the loose coupling, deep coupling, or the tight coupling or ultra tight coupling or deep coupling. So yeah, now I'm going to discuss in this last lectures about the applications of integrated inertial navigation system, more or less. So we're not going to delve more about the theoretical aspects, but we're going to discuss more about the applications of how we do the integrations between the INS, which is the IMU, with other sensors, like for example, acoustics or GPS or others. All right, I'm Fikri Muhammad and welcome to the lectures. Now we're going to talk about integrations. This is the very basic one, which is the integration between the GNSS and the INS. So this applications is not only applied to offshore positionings, but can be also applied in land surveying. For example, if you want to integrate this sensor for drone navigations, that can be also possible, or for the autonomous car for doing the navigations, that's also can be possible. But here, yeah, because it's so common, and as we know that GPS will provide the global positionings to the vehicle, and that's, as we know, that if we are going to apply it in underwater, the GPS signal cannot penetrate in parallel with the depth. So it's more or less applied to the surface vehicle, like for example, USV or ships. So we've already discussed before, the integrations is basically based on the loose coupling and then tight coupling and the deep coupling or ultra tight coupling. Here, the loose coupling is basically using directly the output of positions from the GPS or from the GNSS, and then add it as the measurement input for the INS, and then the INS will integrate this position that derived by GPS and the position estimated by the INS, and then they will update it in the Kalman filter, as we probably previously discussed in the previous lectures. So in the Kalman filter, the inputs of the GNSS measurement will be the positions. And the advantages, of course, the simplicity is easy to implement because we directly use the measurement input from the GNSS. We don't have to deal with the signal that's calculated by the or measured by the GNSS. Yes, both GPS or GNSS and INS operate separately. So they are different things. They're different sensors. They operate by themselves separately. And we directly use the measurement input from them. We don't directly tune all the parameters inside them for the INS for the navigation solutions. And yeah, because we directly use the data measured by them, by both sensors, it of course the computational effort is more efficient and requires less computational powers. And it's okay. Yeah, the robustness is okay as long as it covers enough GPS signals. For example, if the GPS fails, then the INS can continue for a while. But of course, we have to consider the drift. And yeah, disadvantages, of course, in challenging environment when, for example, there are not enough satellites visible for us. This is probably more or less in land surveying, where the multipath exists and the GPS sensor cannot track more GPS, for example, more satellites. And yeah, if it's underwater, then we don't have the visibility of satellites because of the inability of the electromagnetic wave from the GPS signal to penetrate underwater. Yeah, and the limited error compensation doesn't really exploit the GPS signal quality. So it doesn't really, go into the GNSS signal directions, which is applied in the tight coupling and deep coupling. In the tight coupling, the GNSS of pseudo range measurement, so the range between the GNSS receiver to the GNSS satellites, is directly used as an input for adaptive tuning in Kalman filtering. So in Kalman filter, instead of that positions that measured by the GNSS, it uses the pseudo range. So it enhances the accuracy because even though we only have one satellite, for example, we still have the pseudo range input, and it will increase the accuracy and resilience, for example. Yeah, improve performance, improve signal, and it has better accuracy and resilience. And the disadvantages, of course, is increase the complexity because we're dealing with the pseudo range, not the directly, the positions. Positions is more simpler because we directly get the X, Y, and Z, but in pseudo range, we have to calculate it again in our Kalman filtering technique. So we have to adapt it with the GNSS solutions first, and then we integrate with the INS. And because of additional computational task, of course, it has the higher computational cost. And we have to synchronize both of the system, of course, to avoid the latency. And then the last is deep coupling or ultra tight coupling. Well, it has exceptional signal robustness because it directly deals with the signal input from the GNSS, like the carrier phase and also carrier wavelength and also pseudo range. So it improves the accuracies and dynamic performance of the navigation solutions. But of course, it's extremely complex because we're dealing with the signal, so we have to tweak the signals, and which is normally, we do that in the GPS solutions, but we input all that solutions informations to our navigation solutions here, which will add more computational tasks and of course, increasing the computational demand. So for example, in the integrations of loose coupling, we have this, our USV. Of course, we're going to work with robot on the sea surface because as we know, the GPS cannot be used underwater. So here GNSS provide positions and velocity estimate in loosely coupled systems, which will be used to correct the INS predictions, right? And then we directly have these positions here of the GNSS, X, Y, and Z. And as we know from the Kalman filtering, for example, we have the INS predictions. So this is the predicted positions or prediction metrics, include positions, orientations, and accelerations normally. And we have the dynamic metrics that tells the state vectors of where it is right now. So it has the dynamic metrics will basically take into account the positions and orientations and accelerations. And if we have another inputs, then we'll have to add or increase the dynamic, the dimension of dynamic metrics. So it depends to our state vector. For example, if it's only 2D vector, then we'll be having positions and orientation, for example, or positions and velocity, for example. Of course, we have the INS measurement and then the noise that belongs to the INS. And then we have the GNSS measurement. From the GNSS, we'll be having positions and velocity. And then the update of the Kalman filter. We have the Kalman gain, of course, that tells where the dependencies of our residuals or our innovation metric is. So if our residual is close to 0, mean that the Kalman gain will be, or if the residual close to 0, meaning that the Kalman gain is small, that the dependency of the GNSS is not that great or not that much. So we trust to our INS solutions, for example, here, but still we have to tune it with the GNSS. So here we have the predictions of our INS, the estimations of our INS, and then we have the measurement update of our GNSS. And then later on, we subtract them, and then we get the residuals, and then we correlate that, and then with the Kalman gain, as in the Kalman filter. So for example, we want to design the navigation system for USV using GNSS and the INS. And USV states include its positions in 2D vector. So this is in the 2D vector, two-dimensional vector, X and Y only in horizontal. And velocity. So the system uses a Kalman filter for state estimations. And we assume that the USV start at a known locations, which is 0, 0, and velocity, of course, 0 and 0. And then after 1 second, the INS reports an accelerations of 2 meters per second quadrat, and in Y direction, so it's about 2 meters per second quadrat. And after 1 second, the GNSS or GPS reports the positions of 1.8, 1.0. And then we are given with the process noise covariance 0.1, for example, and then measurement noise covariance 0.2. And then we're assuming that our Kalman gain is highly dependent to the GNSS measurement. So that's why it's close to 1, 0.8 for positions and 0.8 for velocity. So if we believe that our INS solutions is somehow okay or good, then we can set the Kalman gain to be 1.0, for example, for both positions and velocity. And yeah, how do we predict the new state from these informations that we get? First, we have to predict the new states as from the Kalman filter equations. And we have to use the dynamic metric F and the INS accelerations to predict the USV state after 1 second or after every seconds. So we include the dynamic matrix F, which is, this is the dependency of positions. Yeah, and then we have also the dependency with the velocity. So the delta time is after 1 second, for example. And then the initial state, we have the, so yeah, the dynamic matrix will be correlated with the initial state. So it has the dependency with the velocity and position. So this is position and velocity. And then we compute the measurement residual to, yeah, calculate the difference between the position calculated or measured by the GNSS and the predictions by the INS. And then update the states using the Kalman filter, basically. And then we'll be having at the end the updated positions from our estimations plus measurement from the GNSS. So yeah, basically the integrations is only in the residuals because we directly input the positions of GNSS as our innovation metrics or residual metrics. So that's basically our integration part in a simpler way. Yeah. All right. And then how we compute finally the updated positions. We first have to calculate the velocity. So we have to meter per second accelerations, right? And then of course the velocity will be 2 meter per second, for example. This should be 2 meter per second and 1 meter per second. And the INS predicts the positions. Then we'll be having in 1 second, because we have because it moves 2 meters per second. So after 1 second, for example, after 1 second, the delta t is 1 second. After 1, of course, it will move to 2 from 0. And in y also like that. So the predicted state vector will be 2. So we'll be having the state vector of positions and velocity 2 and 1 for both 2, 1, and then the GNSS update of the measurement from GNSS, which is 1.8 and 1. So instead of 2, the GNSS calculate or measured 1.8 movement. Then we will measure the residuals, then we'll be having a result as a minus 0.0. So instead of 2, as our prediction predicts, we should have 0.2 meters backwards. And we update the state using the Kalman filters by adding the Kalman gain with the predefined value as we predefined it before. And then at the end, we'll be having the final positions, which is 1.84 and then a comma 1. So the combinations is directly integrate between the GNSS and the INS. At the end, it's not 1.8 or nor 2, but instead of we have the 1.84. All right, that was for 2D vector. Yeah, the final positions is 1.84, 84, and 1. It's closer to the GNSS measurements. And the final velocity is 2 and 1. It's the same as the INS prediction, since the GNSS doesn't measure velocity in this example. And the Kalman filters is basically balances the GNSS corrections and the INS predictions, which is more directly biased to the GNSS or prioritizing the GNSS for positions and the INS for velocity. How about the 3D vector, and which also including the accelerations? Of course, we'll be having larger dynamics matrix. As you can see here, it's 9 by 9 matrix. It has the dependency with the accelerations, half delta t quadrat, and dependency with the this accelerations and the velocity and the positions. So, our state vector will be have positions and velocity. This is position, for example, x velocity and accelerations. And the positions update will be basically derived from the accelerations input. So half acceleration delta t quadrat, delta time, difference of time quadrat. And then the velocity will be dependent on the accelerations. All right, so so from the positions, from the acceleration with gradient, we'll be having positions, and then from accelerations, we'll be having the velocity basically. And the next is tight coupling. So it's basically the same as the loose coupling. So but instead of using the position directly, we'll be having the pseudo range. So because the positions is calculated from 3 or more or 4 or more satellites to determine the accurate positions, but pseudo range will be always having the pseudo range even with only 1 satellite, because it's basically measure the differences for the range between the receiver, GNSS receiver, to the from here to there, or vice versa. So we'll be having pseudo range 1, 2, 3, 4. The more the better. And it's directly used in the Kalman filter update. So we'll be having less dependency on how many satellites that will covered, but nonetheless, the more satellites that use or the more pseudo range that we can put into our Kalman filter update, of course, the more measurements. And then the more measurements, meaning that we'll be having more, yeah, the more accuracy can be. But at least we'll be having more dependency of how we can bring our AI, our estimation to the directly to the true measurement input. And then the last is deep coupling or ultra tight coupling. So instead of pseudo range, we'll be also directly tuning with the signal tracking level. So that's why it's called deep, because it's going into more deeper integrations, which is directly using the signal that receive or signal, yeah, that received by the receiver. And then we directly see through the signals what this look like the carrier wavelengths or the Doppler frequency shift. And yeah, these Kalman filters is also predict the Doppler frequency and phase, because directly this carrier wavelength is uses as we know in the GNSS equations to calculate the distance from pseudo range and carrier wavelengths. So yeah, the Kalman filter update will be having frequencies and also the wavelength of our carrier of our satellite. So as we know, maybe we're not using only one satellite and for example, 4 satellites, and each satellite has it's from different providers, for example, from Galileo, from GPS, from GLONASS, and different satellites has different carrier wavelengths, and the Doppler frequency shift can be different as well. So we'll be having more understanding if we are dealing with a signal level. But of course, it requires more tasks because we have to put the GNSS equations, basically, like the phase equations, then the Doppler frequency shift to our navigation solutions in our Kalman filter. And that's why it will increasing the computational load. But nonetheless, we know that if we want to deal with more accuracies, then we have to look more into detail with into the signal level. All right, so that was just a brief overview of how we can integrate the GPS or GNSS with our INS to increase the robustness and resilience of our navigation solutions. And the other solutions can be possible is with the acoustic and INS. This is the case where GPS, for example, can no longer be used. Or we have another sensor on our ships like LBL, USBL, velocity lock. And loose coupling is basically the same. It's position aiding. So for example, from acoustic positioning systems, it's aiding the positions by determining the range from 3 transponder, for example, with minimum range 3 range measured from 3 transponder. Then we will be having the most optimum positions, because only using one range, maybe it's not as accurate if we have more ranges or we triangulate them. And then in tight coupling, it's the same like GNSS. Basically, it's observations aiding. So instead of directly using the positions, we deal with the range that measured by the acoustics. So it's basically the same. In GNSS, we use the pseudo range. And here we use the measured range. And yeah, in the deep coupling even, we directly use the acoustic signals, and then we have to deal also with correcting with the sound velocity profile as well. So the sound velocity profile and how the range is calculated, and we have to put that. So basically, the range calculation have to be put to our navigation solutions, and also the other parameters like in acoustics, like beam width, pulse lengths, the frequencies, and etc. have to be also put into our navigation solutions. But nonetheless, that will be not be our case here. This is, for example, integrations that been done by Kin et al. In 2023. So for the informations, a lot of integrations between the INS and other sensors is found in the newest or recent publications or recent papers. So it's basically it's also current trends, but because of the complexity, it's also yeah, not so many people are really doing this. So yeah, this will be also the futures of our hydrography. That's why it's very important in offshore positionings. So here they are doing the tightly coupled model. So similar with the INS with GNSS integrations, the coupling methods determine the robustness of positioning accuracy, of course, right? Here they have the INS sensor and the acoustic positioning system of DVL, the Doppler velocity log, and the USPL. So the sensors of GNSS, we have IMU, gyroscope, and accelerometers. DVL is transducer. USPL, the transducer array. So DVL is only using one sensor, right? Because it's directly measure the Doppler shift from the sensor. And in USPL, it has transponder array and transponder. And tightly coupled models from the INS, we'll be having the IMU factor or the step factor or the estimated factor from the INS. Or it derived the linear velocity, the angular velocity, angular rotation rate, and also velocity. Yeah, the DVL is basically measuring the velocity. And then USPL is measuring the heading, like the bearing, slant, and also the angle slant range. And then they are dealing with the cost functions at the end to eliminate the outlier. Or so basically the cost functions is basically the functions to minimize the error that derived by all the sensors. So for example, the INS has the drift, that drift has to be minimized. The DVL has also measurement error from its dependency with the sound velocity and etc. So it has to also to be minimized. The range measurement error has to be minimized. And the SPLs also have the errors that also has to be minimized in the cost functions here. So they're not directly using the positions input that derived by USPL and DVL. That's why it's tight coupled. That's why they are here using the cost functions instead of directly using the positions as an input. So the cost functions is minimizing the error that derived from all the sensors. So that's the cost functions. And yeah, and then the factor graph is basically how the state estimate the predictions, basically how they can predict the next states over time, which also including the bias, which is the factors, the noise, like, yeah. So here they are their test platform. So they have the GPS, the USPL, and also the FOG, fiber optic gyro compass, and the INS. So as a reference, they are using GPS. So instead of using GPS as integrations to the INS, they are using it as a reference. And then all these acoustic plus IMU will be using as the navigation solutions. And all the data is processed in the navigation computer. So there will be their main algorithm that runs the navigation solutions. So they also tested with the common filter loose couple, like the only with positions and Kalman filter tight couple and fiber optic gyro, for example, also loose couple, and their proposed algorithm, which is the vector graph. So yeah, this is their integrated system. Well, this is the INS plus DVL integrations, and then this is the transponder array. Let's see how the data looks like. So basically in their vector graph, they are basically factorizing all the parameters that has to be estimated and also to be predicted. So that's why it's called vector graph. So they are like factorizing all the variables that represent the unknown from random variables and also the estimation problems like whereas the factors represent the probabilistic constraints on those variables and derive from the measurements or prior estimation or prior states. And yeah, it's basically it is the way of how can they do the state estimations and predictions. So it's only that's one way how we can like visualizing how we want to do the estimation later on, because we can like formulate all the variables that has to be included. For example, here we have the prior states. This is for the measurements. So we have the USBL input and DVL, and then this is our state. So we factorizing all the variables that related with the measurements in the prior state, and also the bias. And they do also have the error optimizations, and they also do the factorizations. So, and then the bias will be correlated to the, for example, the NS, and the factor bias is correlate between one factor to another factor. And this is the factor bias in time 2 and then time k and etc. And then this is the factor of INS estimations. And then we have the input from our measurements. So yeah, this is, as we can see here, this is the IMU pre-integration factor. And then this is the bias factor. Yeah, we have the bias and the IMU as in our Kalman filter. And then, of course, we will be having the USBL and the DVL factor. Yeah, that is the way, because we know how we want to chip in our integrations later on. So this is our navigation solutions here in the IRS and the bias, our state and the bias. So because in Kalman filter, as we discussed before, we estimate the state and also we estimate the bias, right? And yeah, that's what they do. And then this is, for example, the trajectory input output from their experiments. And yeah, the loosely coupled acoustic of Kalman filter or KFLC. They do the comparison between that with the tightly coupled and the vector graph optimizations, for example. And then as we can see here, of the accuracy is increased after the initialization state for about 180 seconds. The accuracy is about 0.5 to 0.8. So it's under 1 meters error in east and north directions. But in initial states, as we can see here, the accuracy is still large, but after they are fully integrated, the accuracy is getting better and better over time, or stabilized. All right. So this is just like the comparison between the loose coupling, tight coupling, and the deep coupling. As we can see here, the loose coupling and the tight coupling has more bias in comparison with the deep coupling. The deep coupling is more likely close to the true value of the vehicles under the water, but in the loose coupling, because of the bias and yeah, because of the bias and the drift of the NS doesn't really align with the true value of our vehicle. In tight coupling, it's getting better, but it's still not as good as in the deep coupling. As we can notice, probably somewhere around here, the discrepancy between the vehicle and the true value is larger in the tight coupling in comparison with here in the deep coupling. All right. So you might also try this. This is open in MATLAB. You can click into this link and then see how it goes. We can also try it now. So it will directly navigate you to here. Then you can open in MATLAB online. This is just for fun, and then you can try to changing the values to analyze the differences if you're changing the parameters of noise and bias, for example, or the frequencies. This is, yeah. So then we can just simply run it. It will run, and then yeah, this is basically it has the integration between the DVL and the IMU, and also the GPS for because previously so see here previously the IMU is on the surface, and then it ascending underwater, and then again descending underwater, and then again it's ascending to the sea surface. And then we'll see here, for example, in IMU only solutions or INS only solutions, the drift is large. As you can see here, the RMS error is about somehow almost 6 meters. But yeah, the more sensor, then it's getting better. But the IMU and DVL, it has more or less 2-meter accuracy for about 40 seconds, for example. All right. Then this is, for example, how it looks like. You can try. This is the MATLAB online, so you don't have to have MATLAB in your computer. You can try it online. So this is what it looks like. It has smoother estimations when we are integrating the IMU and the DVL. We can also tune the filter, for example, I guess. And then it will be having smoother estimations at the end. But yeah, I think there's also like parameters that you can define, like for example here, the IMU rate, the GPS rate, and the DVL rate. So the frequency from them are different. So for example, you want to have 30 seconds GPS rate. or more than 5 hertz PVL rate, then you can also change that and then see how it looks like if the error here is better or not. And yeah, you can also try to change the positions, I guess. Like here, the GPS trajectory. Here, the surface trajectory, you can change that if you want to dive in more into this code. But yeah, you can try to have fun here and see how it looks like. All right, so let's go back again. That was the acoustic plus the INS. Now we have another interesting things, which is the geophysics or geomagnetic and the INS. So this is, for example, the example from research in airborne positioning techniques. For example, the geomagnetic navigations relying on the known navigation, known magnetic maps, for example. So here, if we have already known magnetic maps and then we have the magnetometers on board, then we can like mix and match if our position is correct based on the magnetometers measurements. So it's the research from Wang et al. In 2022. As I said, a lot of integrations research of INS with another sensors. It's not, it's like the ongoing trend nowadays. So it's like the current trends, as it's not like globally fully discussed. So more or less it's like it's been started for about a decade or 2 decades ago. So it's not like lot old lot of old research, but it's more about the new trends of positionings because we want to increase our positioning accuracies, and that's why a lot of researchers and yeah, a lot of people are trying to integrate our navigation solutions with another sensors, so like doing the multi-sensor fusion, so that we'll be having the increased accuracy because we don't dependent with one sensor only. Yeah, the geomagnetic navigations is interesting because it's not restricted by time and terrain. So that's okay. It's if there are buildings or if you are under the cave, for example, you don't have signal, but you still have a magnetometers, and the magnetometers directly measuring the magnetic wave in your surroundings, so in your environments, and with the magnetic map, the geomagnetic map that you have, you'll be having more precise informations of where your vehicle is, right? So this is, for example, the track points in the geomagnetic wave between k plus 1, time k plus 1, and then time k plus 2, for example. And at each point represent the where you measure the geomagnetic values and try to like see the discrepancies between the presented geomagnetic values. Like, for example, we see the bathymetric maps on the ships. We are sailing based on the nautical chart, and then we see on the nautical chart is the depth is 5 meters, and then we're our multi-beam, for example, is measuring also 4.8 meters. So somehow we can see the discrepancy between the nautical chart, our base map, the geomagnetic map here in this case, and our measurements from the magnetometers or from the multi-beam in our sailing case. All right. Anyway, normally the vehicle can go only to an area where the geomagnetic map is available for corrections. So this corrections is important because if you're only relying on measurements, maybe it has the error. So the matching and the filtering in the area with magnetic map is important to increase the resilience of the aided geomagnetic navigation solutions. This is the case when we are only relying with the geomagnetic measurements for our navigation solutions in our area. Without magnetic map, that will be a little bit difficult because the geomagnetic gradient navigations is a bit biased because of the noise and the bias. So yeah. All right. So the integrations here, the systems is basically adapt based on the availability of geomagnetic data. First, without map, uses the geomagnetic gradient bionic navigations is basically like you are relying on your nautical chart to guide the aircraft. And with map, that combines the geomagnetic map data with the simultaneous localizations and map corrections, SLAM. Here, to refine the INS accuracies. So yeah, as we can see here in the flow chart, the INS will try to chip in with the geomagnetic map analysis. And if we don't have the geomagnetic map, then we have also to integrate with the relying only with the geomagnetic measurements, and then we achieve the destinations at the end. So but if we have the geomagnetic map, then we try to like matching the features, matching the values from the geomagnetic map and the measurements from our geomagnetic measurements from our magnetometers, from our MAGI. And yes, that method is called as a simultaneous localizations and mapping. So it's basically in real time, simultaneously, we do the localizations based on our MAGI measurements that directly match to the map. So we're relying our positions to the maps, basically. Yeah, so because we have the best map. That's why it's called the simultaneous localizations and map corrections here in this case. And yeah, of course, the error from this will be chipped into our INS solutions at the end. We'll be having that integration of our INS between the error or the residuals from the SLAM of MAGI between the INS. So this is, for example, the INS and MAGI matching integrated navigation correction results. With MAGI map is in the front sections. So this is the area that we have with the MAGI map, with magnetic map. And this is the area without the map, which is also our destination at the end. Yeah. And so yeah, when we have, so this is, for example, the line here is the navigations of a MAGI. So if the aircraft has base map MAGI, for example, have MAGI as a base map, the navigation and the INS they're like aligned to each other. But if it's not, then it has a little bit, yeah, it has bias that will be later on be corrected to go direct to the destinations. So this is the position corrections at the end. This is, for example, the INS output is the blue stripe lines. And then the corrected trace is this one, which is also our desired trace, our designated tracks, for example. And this is the geomagnetic profile correction curve in integration with the INS. So for more details, you can read through the papers. And yeah, this is also not that common. I haven't also tried the integration between the geomagnetic, between the MAGI and the INS before, but somehow it can be possible. But yeah, that we can gain from this information, that is, if we have a base map, like the mega map, geomagnetic map, it will increase the accuracy because we can do the SLAM methods, like we are matching where our measurements to the actual geomagnetic curve positions in those areas. For example, here we'll be having like the discrepancies between the INS output and the estimated later on estimated output. All right. Okay, the next one is the optical and the INS. This is also the current trends nowadays because a lot of underwater vehicles are nowadays equipped by camera or lidar as well, or laser. Because as we understand that in some point the photogrammetry techniques, like in the optical methods, we can get really good models from that. And yeah, the optical is basically based on the photogrammetry methods. So it's basically measuring or try to triangulate the object that detected in the by the camera. And then if we are only using one camera, we have to move the camera a little bit so that we'll have the another image. And from that two images, basically based on the two images, we can do the feature detections. So we can like see what kind of objects in our seabed and project that object to our camera and do the triangulations. Is basically like SLAM in geomagnetics, we're basically determining the camera positions based on the object on the seabed. So we basically create a map, like in photogrammetry, we create a 3D model, and then from that 3D models, we determine the positions simultaneously. So that's why it's also SLAM, the simultaneous localization and mapping. It's the same as a geomagnetic, but instead of we are relying on the predefined or previously available map data, we're here creating the data in real time. So we're creating the data and simultaneously estimating the camera positions. So we have two tasks here. We create a 3D model, and then from the 3D models, we'll directly also measure the camera positions. It's basically like the photogrammetry, and photogrammetry is basically like that. We're dealing the bundle based on the bundle adjustment. So like in bundle adjustment, you directly in photogrammetry, you directly do that simultaneously, but it can be also in photogrammetry. Basically, we are determining the camera positions and our object, right? But how we can do that in real time? Yeah. So here the SLAM is for real time purposes. So you're doing that sequentially, from one camera position to another camera position. From each positions, you like doing the photogrammetry or doing the bundle adjustment iteratively every time. And yeah, you like doing the photogrammetry in real time, basically, instead of doing the photogrammetry from all the captures image. And it was for the mono camera, we have to move the camera a bit by a bit. In the stereo camera, is basically, two cameras placed in the camera rig and with known dimension, with known distance. And because the distance is known, we can have the metric information. So we can later on generate the metrics information. Previously, in monocamera solutions, we'll be having only arbitrary positions estimation. So we have to correlate that with the INS later on to have the metric informations, because the INS is basically measuring the velocity, accelerations, and both of them can be measured as metric. And if we are integrating the mono camera and or camera with the INS, we'll be having the metric information later on. But here, the stereo camera can generate the metrics informations. So metric means like if the object is cube with 0.5 by 0.5 by 0.5 dimension. With the stereo cam, will be able to retrieve that dimension. So this meters informations. But in mono camera will be like having wrong scale. So yeah, it's basically capturing two images simultaneously and detecting the features simultaneously, and then also doing the projections from these extracted features to our camera positions and estimate the camera positions. So this is just for example. Oh. Yeah, this is just for example. This is the slab. So we can see here the camera, like this is the camera. This is the camera positions. And simultaneously, it also create the 3D point clouds of the seabed of here, the coral reef, for example. And but of course, the drift will be also always increasing over time, because like in photogrammetry, we're like circling around the model to derive the 3D models. But here, or we have to have the side lap and overlap to mitigate, or we also have to have the ground control point to mitigate the drift accumulated over time, so to increase the accuracy, like for example. But here we don't have anything, we just rely only one camera. And of course the drift will be increased over time. It should have to go to another position, as you can see here, because of that because of the loop closing functions that activate in SLAM, in the optical solution navigation solutions here. Yeah, as we can see previously, go that way, but after it find a similar image that measured previously, it closed the loop basically. So it has the loop closing functions, which is correct or minimize the global navigation solutions at the end. All right, so how do we integrate it? Well, it's basically all the integration is somehow the same. So either you do loose coupling, deep coupling, or tight coupling. Oh yeah, loose coupling, tight coupling, or deep coupling. You're like basically, yeah, dealing the same. In loose coupling, you're just directly relying on the positions that estimate from both sensor. And then more tighter and deeper coupling, you are directly measuring the signal inputs from the sensors. But first, as you can see here, we have here in our AUV the MEM sensor and the stereo camera sensor. That is, for example, our IMU and our camera. We have to determine the relationships between the camera. So relationships is basically the transformations between frame, the offset and transformation between frames, between camera and IMU frame. We can do that by using by doing the calibrations of IMU and camera. So like moving in each axis to determine the relationship between the frames. As we know in IMU calibrations, we'll be also determining the relationships between the camera and IMU frame later on. And of course, we have to calibrate the camera and the IMU, like estimate the sensor noise, estimate the parameters, the internal parameters of the camera, and yeah, before we can use that. Yeah, you can also try to do this and investigate how it looks like. So this is, for example, monocular visual inertial odometry using vector graph. In our optical navigation solutions, we have images and detect the key points and track the key points and triangulate the, as we know in SLAM, and estimated the camera positions. And yeah, we'll be having the camera factor, which is the pose positions and 3D points. So we have positions for seabed and the camera itself. And then we do the factorizations. And then in IMU, we have the camera and IMU alignment. So the relationship between frames and the IMU factor. Yeah. So this is for example. So you can see here the integrations between the IMU inertial with the camera. As you can see here. So the camera pose is the dark blue one. And then the IMU is this one, this green line. And yeah, it's directly measuring or creating a map, like in photogrammetry, creating the 3D models, which is denser, as probably measured by the acoustic, because sometimes the acoustic will returning its backscatter noise that will degrade, of course, the accuracies of the models. But here in the photogrammetry, it's relying like only with the object that detected by the camera because it's optical, so it doesn't have the backscatter noise as is in comparison with the acoustic. All right, and then the next is the multi-sensor navigations. This is also the current ongoing trend that it hasn't really been discussed. But yeah, it's ongoing trend because it's complex, because we have to deal with a lot of input from the sensor. So a lot of different sensor, we have to deal with that. And if you're going to do the tight coupling, then it means that we have to really take it into account into the what kind of factorizations that we have to deliver, what kind of variables that we have to deliver, that will be increasing the large dimension matrix at the end. So for example, here, this is from Rahman et al. Yeah, this is multi-sensor integrations between INS, visual, acoustic, and pressure. It's underwater, so that's why we don't have GPS input here. And we have the stereocam, and then IMU, the pressure, and the sonar. And the camera will do the image processing, like doing the camera positioning with like photogrammetry, the pose estimation from camera motions. Of course, it detect the feature first before it do the pose estimations. And then what's real interesting here is that they are doing the tight coupling, meaning that they are directly deal with the reprojections error or the error that accumulated in its sensor. In the camera, for example, is the reprojection error, meaning that the error that deliver from the projections of the points, so the points is detected on the seabed and then they projects to the camera, right? And then of course it's not directly reprojects to the true positions of where it is in the camera in the pixel based image. So the image will detecting the object, but maybe the pixel will detecting some errors, so it has some pixel error. So it is the projection error, and then the IMU error, of course, the state estimation error, and the depth error, for example, it has to detect in if the AUV is diving 1 meter, for example, the pressure is only detected 0.98 meters. Of course, it has depth error and also the sonar range error. And yeah, so it's very interesting here because they are dealing with the error directly instead of doing it loose coupling, like using directly the measurement output from each sensor. And yeah, at the end, they do the post optimizations, like in the cost functions. And after that, they can do the loop detections and post-graph optimizations. All right, let's see how it goes. So let's see how it looks like. So this is, yeah, their algorithm. It's called as FIN2. This is multi-sensor fusion based underwater SLAM systems. The robot sensor include here, as you can see, the sonar plane is downward-looking sonar, and then camera field of view, forward-looking camera, and it has also pressure sensor, of course, inside it. Yeah, and IMU as well, the MEM sensor. So they're doing tight coupling non-linear optimization. So in simpler way, they are directly dealing with the error estimations, so the projection error from the camera. So this is cam. Yeah. And then this is IMU. And then this is sonar. And then this is pressures, because it's basically based on the robot positioning state in the gravity directions, or yeah. This is pressures, yeah. And this is sonar and the IMU. So yeah, all the sensors are chipped in together, but of course it has its own error, and this error is the way they integrate to each other. So by doing it here in the cost functions, so this is their cost functions, or their functions basically, to minimize the error. If we have minimum error for each sensor, meaning that we have, of course, good estimations, because our estimation then will be correct. But first, the error has to be minimized first. Like the reprojection error is that of some pixel has to be minimized. The error, how we minimize that, all of the error is basically we do the iterative. We can do it in a model, or we can add more measurements each time. So if we have high rates of data recording, of course, we'll be having more accuracies, then we'll be able to tackle the error or minimizations this way, or by doing it with models or mathematical models, like doing it iteratively. So first we do the projections between one point on the seabed to the camera, for example, one time, but we're not doing it one time. We iterated it, iterated again until several times, until the error become less and less, and then yeah, then we'll get the optimizations at the end. Okay, this is, yeah, their output. For example, this is the case of sunken bus in the United States. And yeah, this is inside the bus, and then this is the reconstructions from the multi-sensor integrations. This is the yellow one is their pose, also the robot pose, and the red and green point clouds is basically the inputs from visual and sonar features. So it's somehow robust with 2% error in centimeter level. So centimeter level, 2 centimeter error. So it's really useful if they are like doing the navigation inside the bus here, which is also not that large, and it's not open. So it's very useful if the robot want to investigate the cave, underwater cave, for example, or the archaeological information here, or man-made platform like oil rigs that has to like navigate inside the platform. It has to have the precise informations of navigation solutions. So that's why the centimeter errors is really good enough to to navigate inside this tight or narrow environment, like inside the bus, for example, here. Because otherwise, if we having like based on the IHO order, for example, with large horizontal error, then yeah, it'll be difficult for the robot to navigate. And then the submerged bus, also in the US, as we can see here, this bus is somewhere around here, and they're like circling around the bus, and also they're going inside the bus. So it's really have to have good navigation solutions because they're like channeling inside the bus door. So they're going into the bus door, for example, here, and then going to outside into the bus door. So yeah, of course, the navigation solutions is very important here. Otherwise, the robot will be stuck inside the bus. We cannot go out if the navigation solutions is not that accurate. And they are like doing the comparison with other solutions like Colmap is the photogrammetry open source software, and Spin their algorithm. This is their algorithm, and they're comparing with other methods like the monocamera integrations with visual inertial. So this is only like inertial NS. So it's only like ENS with monocamera. And this is also the same, INS also. Without accumulating the pressures and also the acoustics, of course, as we can see here, the red is okay, but in slum, so the slums is basically you can do the integration with the INS, but I think they are here only doing the stereo camera navigations, and it's resulting in not as robust as the other methods that integrate with at least one sensor. So inertial with camera has more accuracy in comparisons with only with one camera, but they don't have here the inertial solutions only. So the OCVIS is also INS with visual sensor, which is not that reliable, but yeah, it's based on their mathematical model. So the call map, which is also interesting, is somehow close to their approach. So this is their approach, the green one. And then the column of the photogrammetry is somehow close, but not that that's close. So there they are like lost tracking. Inside the bus, they are got lost. The photogrammetry methods is not able to detect more features, for example, and then the vehicle got lost. That would be very dangerous, right? If you're like doing the navigation underwater. But anyway, the column of the photogrammetry is not able to recover the positions here. And yeah, the call map is interesting. The photogrammetry is interesting because instead of their doing it real time, the call map is doing it in post processing. So it means that they are not doing it real time. Real time means that you like estimating your value or your positions based on the previous one, right? But call map is estimating your positions based on all the estimated positions. So you have already all the database, and it's way more easier if you want to estimate where you are from all the database that already been measured or collected in comparisons only with yeah, doing estimation sequentially over time. And then this is also the same. This is the cave environment. So they're like doing the navigation inside this narrow cave, which is also very challenging environment for the robots. And as we can see here, the fins mono even only integration between the inertial sensor and visual has bias or has more errors, just about meter more. Yeah, in comparison with their solutions. But somehow, yeah, that's okay enough. But yeah, that has to be noted here that more sensors that integrated to their solutions mean that they will be having more dependency to another sensor instead of doing dependency with only one sensor. All right, I think what you can try is also try to go here. You can take a look how it looks like, and then you can also open it in MATLAB online and then try to run the code as well. And then see how it looks like. Yeah, this one. So, but yeah, it's doing the integration between visual and IMU or INS with the drone, with the copter. But anyway, the quadcopter. It's yeah, for land surveying, but still it's relevant to our case. You can try to run it. And this is the algorithm. And then this is, for example, data. Yeah, you can try to change the data. This is, for example, the visual outputs of the camera. They have enough parallax, means that they have enough features between one frames, one image to another image. So they have enough parallax. So they have like enough match features between frames. Then they do the triangulations. I wonder if they have, yeah, this initial structure from motion. You can see here some point clouds detected by the camera in initial stage, and then doing the camera and IMU alignment. So this is the before alignment, and then after alignment, you can see here it's somehow close to the ground truth or to the true value. And yeah, this is the estimated trajectory at the end. And the trajectory with the landmarks. Landmarks is like the detected features. So, right, this is the initial stage where the AUV capturing the first frame, and can do also the comparison between the ground truth and the estimated trajectory. And yeah, you can try to change some parameters and maybe also changing the directions. I'm not sure if it's not possible because it's relying also with the image input from the MATLAB. But anyway, it's fun to try this. I can see why not. And I think that summarizes all the modules of integrations, inertial navigation systems. And all right, I hope you got some info of how we can do the integrations between the sensor. But the thing is, we have to rely on the coupling methods, of course. The coupling methods will define how our integrations method is. And from this, we can see how much we can trust to our estimation later on. All right, I think that's all from my side. And thank you for joining the lecture, and see you next time. I'm Fikri Muhammad, and I hope to see you next time. Bye-bye.